In this module, we will discuss the calculations of the two most important petrophysical properties that help in reservoir fluid volume calculations. These are porosity and water saturation. Density log is one of the most common logs for porosity calculation. Sometimes the neutron porosity and density porosity values are also averaged for porosity calculations. Let us see how to calculate the porosity in a well using these methods. Go to the calculator and basic log functions, and then we can go to density porosity. And let's at the same time display our log that we had before. So file, load plot format, and we have this plot 1 open. Let's remove these ones for now. So we have our well log. We have this heater, upper Hugein, middle and lower Hugein and Sleipner formation. And let's create a new track for porosity here. Okay. So let's calculate it for the heater and formation above. So we will enter the top depth, which is about 3100 here, where the logs begin for NP and rho B. So 3100 up to top of heater formation, which you can see is about up to the top of the upper Hugein formation, which is about 3245.4. And since the well is mostly sand and shale, so we can keep the matrix density to 2.65 and the fluid density up to here, to this point, is mostly water, so we can keep it 1. And we have other methods of calculating porosity, but we will right now only use density. And again, the output set would be the calculated set. Okay, so now we can run the tab, and let's see if it created something. So you have the calculated here, and we have the density porosity, and we can do it from 0 to 0.5. And the porosity has been calculated from that point up to heater bottom. Then we know that this is a gas zone, so let us calculate the porosity from this that point up to bottom. So we can just use this one and choose let's see, we can choose the tops, and we can choose the Sleipner top to Sleipner bottom, okay, and keep the same inputs. Okay, so it automatically adjusted the depths. Okay, and then run the tab, and you can see porosity log was created here. And in between here, which is our gas zone, we can choose the depth. That's the top of upper Hugein is the top, and lower Hugein is the bottom. Okay. So bottom depth is about 3305, which we see here. Okay, and the top depth here is upper Hugein, so 3245. Okay, so this is correct. And since we know that it's a gas zone, so we can start with a really small fluid density of, let's say, 0.1. Okay, and then run the tab, and this is our porosity here. And then one thing we can do is compare this with the pore data. So we have the porosity in the pore, we can drag it here, okay, and adjust the scales. So we just keep the same scale as the log, and then here we just make it dot dot. So now they are plotted here. So you can see currently we are underestimating the density porosity. So probably if we increase the fluid density to a higher value like 0.2 and run the tab, you see it's increasing. You can increase to 0.5 and run the tab. You see it's increasing. But one thing you should remember is that we know pretty well that we do not want to play with the matrix density because it is a sand stone. We can adjust that, but we don't want to do that. And also we cannot have too much latitude with the fluid density as well, because we know it's a gas zone. So let's say if we just use one like water, then you see it overestimates the porosity. So uh, so instead of doing this, we can do we can try to use another formula that we knew before. I think we will combine the density porosity and neutron porosity, and for that let's calculate everything from the top to bottom using a fluid density of 1. So let's say like a 3100 up to the bottom. Let's say like just put any number like a 3700, and calculate the whole thing using these inputs. Okay, so run tab. Okay, so it does not change because everything was 1 to begin with. Now now we will use the calculator. Okay, so we can go calc and user formula. If depth is greater than 3245 and again depth is smaller than 3304, then we use the formula NV square plus our density porosity square divided by 2 to the power of 0.5, means taking the square root. Else it is NV plus our calculated density porosity divided by 2, and the curve set, let us name it PHI neutron density, and the output set would be the calculated one. Units would be decimal. Okay, so what this basically means is that if the depth is between here and here, then use this formula. Otherwise, use this formula everywhere else. Okay. So if everything looks good, then we can run it, and you see it created a PHI neutron density in the calculated folder. Okay, so let's close it and let's plot it here. Okay, Let's change the scale. uh, let's make it a different color. Okay, let's make it red. Okay. uh, so what do you observe? What kind of observations you make? So this is our original density porosity calculation, okay, in blue, and this is the, in red is the combined porosity coming from neutron and density logs, neutron and yeah, density porosity. So you see the match is very good here with the core data, the red one, compared to the blue, which is the only density porosity. Okay. So one thing you should observe here is in the shaly zones, the combined porosity from neutron and density is higher compared to only density porosity. Why? Because in shales you have water, which increases the neutron porosity. So when you use both neutron and density, then your porosity will be higher compared to when you're only using density porosity. But in the sands, you see these values are much closer between blue and red, but the red values are closer to the log calculated porosity. Sorry, to the core measured porosity. And you see here in this Leitner formation too, the red one is a bit closer to the actual core porosity, the modified core porosity, compared to the blue one. The next important petrophysical property is saturation. Generally, it is the water saturation that is calculated from logs. Water saturation is then subtracted from 1 to calculate the saturation of any other fluid that may be situated in the pore space. Simplest method to calculate water saturation is the Archie equation. In clean, non-shaly sands, this equation works very well. However, as the amount of shale in the sand increases, this method overestimates the water saturation due to increased electrical conductivity in shales. In this example, we are mainly interested in the clean sands, so we will use Archie's equation. Now, let us look at the steps for water saturation calculations in IP. We will go to calculator and basic log functions. So we will choose the RW apparent SW. So this is the tab. And since we have already calculated the porosity, it should appear here. We will use the PHI neutron density. So we use that one. Okay. Sometimes this will not be auto selected, so you have to search it from there and then select it. And then we will choose the true resistivity curve, and RXO, which is the flush zone resistivity curve. You can select that if you have, otherwise it is not required. Then use the porosity calculated from neutron density from the combined logs, and for the temperature, since we have already calculated the temperature here, so we can use that curve. However, if you wanted, you could enter some number here, but since we already have the curve, so we will not use a constant number. Okay. Then we will choose the temperature in Celsius. Remember that if you don't change that Celsius or Fahrenheit, the calculations will be wrong. Okay. Okay. And why do we need that? The temperature curve is needed to extrapolate the brine resistivities to different points in the reservoir using the ARPS equation, which is RW, or resistivity of water at temperature 2, equal to resistivity of water at temperature 1 times temperature 1 plus 21.5 divided by temperature 2 plus 21.5, and this is in Celsius. So the brine resistivity reported in the data set was 0.07 ohm meter at 20 degrees Celsius. So let's change this to Celsius. Okay. And we don't have our mud filtrate, so we don't use that. Okay. Then one thing about Archie's equation is that if you are using this in a clay-rich zone, you will almost certainly overestimate the water saturation. But since we are mainly focused on the sands, we should be okay. Okay. And then you have to choose the AMN. What is A? A is the tortuosity factor. M is the cementation factor or cementation exponent, and N is the saturation exponent. Okay. Okay. We can for the outputs we can choose the Archie formation factor. And what is that one? That is A divided by porosity to the power m. So A divided by porosity to the power m is the Archie formation factor, or it is also the ratio of resistivity of rock filled with formation brine and the formation brine itself. Then we choose the apparent formation water resistivity, which is porosity to the power m times the resistivity. And how do we obtain this? This is obtained by using the Archie equation and setting the water saturation equal to 1 and A equal to 1. Apparent resistivity in a clean rock saturated with brine is the same as the R sub W, which is the brine resistivity, right? So the AMN values, when we plot the water saturation, they need to be modified to match the core water saturation. So let's plot, let's run it and then plot the water saturation. Okay. One more thing here, we will choose the water saturation Archie, okay, because that's what we are calculating, and the output set will be calculated, and the depths, even though we can do it for each zone one by one, but in this case we will do it for the entire well at once, so we will just keep them blank. Okay. So if everything looks okay, then we can run the run tab, and it should create something in the calculated. It should create something called these three: water saturation Archie, so FFRWA and SWRG. Okay, so run, and it created those three things. Okay, and these are arranged in alphabetical order. So FFRWA and SWRGs, those three things are created. Okay, so now we can plot them. So make some space here. So new track, and make some space. Okay, so let's plot the water saturation Archies, and generally I like to plot it from 0 to 1, and you can have your own preferences. 0 to 1. Okay, and we should also plot the core water saturation, so we'll plot it here, and use dots to represent the core data. So all of them are here. Okay, so we need to match that using and by playing with the AN values. Okay, so we ran it with the default cases of 1, 2, 2, which is the most default case people generally use. Okay, okay, so now let's see the effect of AM in here. Okay, so let's change A to what? let's say 0.8. Okay, and let's use okay, let's see what happens. Okay, so run tab, see all the curves move to the left, and if we use like a uh, 0.8, let's say 2.1 and 2.3, and make a run tab, you see now there's a better match with the data, the core data. Okay, so look at this. So these values that we are using here are within reasonable for sandstones. There may be slight variation, but they're quite reasonable. And one thing about this one, if the oil wetness of the rock increases, this value can go up to 4. Okay. Again, it is rare to see perfect matches with the core data. As long as you get a satisfactory match, you should be okay. So here we are getting a match in a Heather formation, Sleipner formation. Okay. Okay. One thing you should notice in this interpretation is that wherever the gamma ray is low, which is clean sands, we have very low water saturations, as you can see here. Okay, how much? Like low water saturations, and the lowest water saturation could be 10%, 15%. Okay, here we have slightly lower, but this is just for demonstration. And if we have high gamma ray values like these ones, which are more shelly, then you will see high water saturations, like close to 1. Okay. Sometimes you will see in shalier zones, you can see water saturation greater than 1. Okay, that's not exactly true. If you see values greater than 1, you can assume it's like a 1. Okay. And since we are performing the conventional log analysis, such as mostly in sandstones, therefore water saturation in shales don't really matter. And if you go into these shales, the water saturation can be far off, because in shales we need a different kind of analysis, petrophysical analysis, which is called shaly sand analysis. Okay, uh, but uh, but that kind of analysis is an art on its own, and we will not discuss it here. And as long as we get reasonable values in the sands, we should be okay. So one thing here is that if you keep increasing the values here, for example, I'm just using some ridiculous values just to show you the trend of the movement. Okay, so if Archie's factor goes to 2, so you see everything moves to the right. Okay, so let it put it back. Okay, if you similarly change this from 2.1 to 3 M factor, okay, see everything moves to the right. Okay, let's put it back. And then similarly, if you choose this 4, okay, and the N values, then see everything moves to the right. Okay. So let's put it back to 2.3. So what you see is the Archie's equation is such that any increase in these values will pull these curves to the right, the water saturation. Okay. One more thing is if you change this neutron density porosity, if we just used the density porosity and run the tab, you see the saturation, water saturation goes crazy in the shale. Like it goes high up, like 1.08, 1.32. You see it's way above 1. Okay. Why is this the case? Because if you remember, the water saturation, the porosities, the density porosities were lower than the neutron density porosity, correct? So lower the porosity value, higher the water saturation. You will see the Archie's equation, and you will see that lower the porosity, higher the water saturation. So let's change it back to neutron density porosity. So If you want to increase these values a little bit, you can use 1 here. Okay, but I'll keep using 0.8 because these values here like could be a bit low. Okay, but let's use that one. Okay, anyways, as we already mentioned that in the shales these values are quite off. Okay, but how about this Sleipner formation? The Sleipner formation is slightly shaly to silty. Okay, it is mostly sand but slightly shaly to silty, so the water saturation may be off here but not far off from what you see here. Okay, so how do you know that it's slightly silty or it's not exactly shale? Because if you look at the crossover between N-Rob, there's almost a good layover, even though we can see some green color which is shale. But if you compare this to the actual shelly zones, you see high gamma ray here, actual shelly zones, then it's here the the shale indicator, which is in green, is much higher. Sorry, I called it crossover. This is not crossover. The green means shale indicator and red means crossover. So there's low shale and there's high shale here. Okay, so you and this scale that we are using here is in limestone porosity unit. If you want to change it to sandstone porosity, you just have to put it back, change this to 0.6 and 0 and 1 point. Okay, let's cancel it and make another one. Let's see if we can make another one. We will just duplicate the track, and here we will display the sandstone scale. Okay, so 0.6 to 0 and 1.65 to 2.65. okay, and you see now this is in sandstone scale, sandstone porosity units, and you can see the shale indicator green color has increased, but so in the Sleipner, but so it did in the shaly zone. Okay, so the shale indicator increased and the crossover, which indicates gas, decreased a little bit. See, compare this to limestone, this decreased a little bit. Okay, so in any case, if you compare a pure shale here, which is close to pure, and this Sleipner formation, then it's much less shalier. Okay, so therefore the Archie saturation will yield some saturation which may not be too far off. Okay, so let's delete this curve. Okay, before deleting, you can see that in some zones in the Sleipner, you can see there is almost a good layover between, in both scales, there is a good layover between N-Rob. Okay, this means these sands are cleaner within the Sleipner formation. Okay. Okay. Okay, I would like to show you one more thing. I would like to show you the apparent resistivity method. Okay, so this apparent resistivity method is a quick look method to detect hydrocarbon zones, which is done in early part of the log analysis. So for this one, first we will calculate the brine resistivity curve from the given information. So we will go to calculator, user formula, and so let's calculate RW, and the formula would be, as I mentioned before, it's a 0.07 times 20 because the resistivity data was given at 20 degrees Celsius, plus 21.5 divided by the temperature curve. Where is that? okay, divided by, oh no, we will not use this one. So temperature curve here, sorry, temperature curve plus 21.5. Okay, uh, so this is the ARPS equation that calculates the resistivity, the brine resistivity, and then the output set would be again calculated. Okay, yes, and decimal, and we will do this for the entire well. So we don't use the else formula, and we don't use any numbers here for the depths. Okay, and we should remove any if condition here. Okay, otherwise it will just calculate in that depth. Okay, so this should calculate something called RW in the calculated folder. So run. Okay. So it calculated the RW there. Okay, so now make a new track and plot the RWA and RW. Okay, and again they should be in the same scale. Okay, so let's make it from let's say 0.001 to 1000. Okay, 1000. Okay. Let's check. We should use the log scale for both. Okay, so this is your RW value that we calculated using ARPS equation, and this is your RW apparent. So how do you interpret this log? So you see, at the reservoir temperature, the RW value, just look at the values here when I put the cursor here. So RW value is about 0.02 and RWA is about 0.01. So those are very close values, as you can see from here. So at the reservoir temperature, they are almost the same. This means what? If the RW and RWA are very close, it means that zone does not contain hydrocarbons. If you go to this zone where we have the hydrocarbons gas, then you see there's a huge difference between RW and RWA. Okay. So RW is again close to 0.02 and RWA is how much? 0.8. Okay, 0.8, 3.85, 5.8. So it's more than 200 times this RW. Okay, RWA in these zones is more than 200 times. This means it's a very sure shot indicator of hydrocarbons, given all other conditions are satisfied, such as it's a sandstone. Okay, it's a high porosity sandstone, and generally the rule is that if RWA is greater than 3 times RW, then there are some chances that there is hydrocarbon in that zone. Okay, let's move up. You can see RWA is very high here compared to RW, but look at the lithology, it's a shale. Okay, so we don't care anyways, because just this is not this only condition. We also need to see if it's a clean sandstone, high porosity sandstone or not. So yeah, so we will ignore this zone, even though RWA is much greater than RW, but this zone is important. One more thing about the ARPS equation is that we use 21.5, 21.5, right? Because we are using Celsius. If you use Fahrenheit, then instead of 21.5, that number would be 6.77.